Hey, what's up, guys? Yeah, welcome to my own complexity theory video. And previous video I defined MA basically is Merlin Arthur, and I also define AM, so it's Arthur Merlin. Right, so intuitively is that Merlin Arthur basically Merlin send a message to Arthur, and Arthur has the high probability to accept if the answer is correct, and if the answer is incorrect, then whatever Merlin sends, then Arthur will say no. Okay. So Arthur Merlin means that Arthur sends some coin to Merlin, and Merlin replies a message, and whoever Arthur just run it, and Arthur need to determine it. Okay. Okay. So maybe a little bit non-trivial fact. So I will I will make few videos about this MA and AM because this now I think it's very interesting. So non-trivial fact is that MA is a subset of AM. Okay, so this is what I gonna to talk in this video. Okay. So before we prove this, and before we prove this, that hopefully I still write down a definition again, just for the convenience. Should be very quick. Okay. So you have two polynomial P of n and Q of n, and then for the let's assume that we have these two polynomial, and the MA, right? MA means that if x belongs to L, then there is a z. The z length is Q of n, and okay, there is a z, and the probability of y. So length of y, this is the length of y is, let's say P of n. So y is so MA means that the Merlin, right? So this z is a message, and the probability y is the random coin that Arthur choose. The probability of x, y, z. By the way, this is a probabilistic term machine which takes three inputs: x, y, and z. Output 1 with high probability. Okay, if x do not belongs to L, then for every message that Merlin sends, then Arthur will reject. Arthur will reject with high probability. Okay. So this is the Merlin Arthur. And how about Arthur Merlin? So Arthur Merlin is this. Right, if x belongs to L, right? So Arthur send a message, right? Arthur send a message, and Merlin reply. Oh, Arthur send random coin, then Merlin reply. Okay, so this write down should be write down is this. The probability y, right? This is Arthur random coin, right? So Arthur send a random coin to Merlin, and then there is this the message that Merlin can reply, right? Is this a z? And n of x, y, z, of 1 with high probability. And if x do not belongs to L, then the probability of random coin for every message, for every coin that the Arthur sends, Merlin cannot make this algorithm accept with high probability. Okay, so yeah, so these two are basically the definition, hopefully, and the lengthwise Q of P of n and let's see as Q of n. Okay, so the goal is to prove that the MA is subset of AM. Okay, so the goal is to prove MA is subset of AM. Okay, so in order to prove this, the idea is just the same as BPP. You just use the arrow reduction. Basically you try to reduce error. Okay, so the idea is very simple that the author, right? So Merlin give the author message, right? So author can do a thing, right? Author can repeat the algorithm for many times. Okay, let's say more precisely is the following. So we know that there's a random bit string that author can make this correct, right? So author can just copy Merlin message. So Merlin sends z, right? So author can, let's say author can copy z, right, for a lot of time, and author can just run this algorithm. Okay, author can just run this probabilities of y algorithm. Okay, and take a majority vote. Okay. So more precisely is the following. Right? You can define you can say this algorithm output is xy. So it's xi. This is outputs xi. Let's say you do a lot of rounds with every round 1 to 2 up to maybe n. Okay. And the mi output xi. Okay, so xi is a random function, right? So you can take. Okay, so you know that there's x to be summation of xi, and the xi random variable defined to be 1 if m of x, y, z just output 1. Okay. Otherwise that is 0, right? So just this, and you know that the probability of this success is 2/3, right? So okay, so you can ask the following. So this means something. This means that the number of z, right? The number of experiments such that probability of this equals to the number of the expectation value of the success the number of success in the experiments should be greater or equal to 2/3 times n. Okay, so this means that right, so you can ask what is the probability that say x minus expectation value e greater let's say that's greater than equal to let's say 1 divided by 3 times n. Okay, and you can prove this using the Chernoff bounds, right? Because you can prove the Chernoff bounds, so it's 2 exponential something. Let's say maybe it's the n time divided by some constant. Okay, so since you use, I think more precisely you can use Chernoff bounds, but this is the same as PVP reduction, right? So you can prove this, right? You can say that okay, you can easily you do things and you make the error like very small. Okay, so on the other hand, if x will not belongs to L, then if you do run this, then the number expectation is 1 divided by 3. So you can use this take majority votes and reduce the error. Okay, so simply speaking, that once you do this, then you can make this MA to be more powerful. Okay, so let's just write. So and notice that the z is always the same, right? Z is always Q to that because Merlin saying it, but also you can just copy the Merlin's results and only use the exponential of times. Only use the polynomial times of n, then one can reduce the error to the following. So I think for the convenience, I will choose Pn plus Qn. So it's very large, and then this is very small. Okay, so this is my my error reducing version. Okay, so I want to claim that this will implies this. Okay, so this will give us the proof of MA subset of MA subset of AM by just choose the same M. Okay, and the same Y. That's it. Okay, so let me just do a proof. Okay, so now we have so now we can prove this. The proof if x belongs to L, then what I need to give you the AM protocol, okay? But it's a trivial, right? Because whatever Arthur sends, Merlin replies the same message, right? So in this case, that Merlin sends Z, and the Arthur just Merlin sends Z in the MA case, right? But in the AM case, that whatever Arthur sends, Merlin just replies the same Z. So you don't want okay, so there's a message that Merlin sends into Arthur in this case, right? But in this case, that Arthur sends some coin to Merlin, and the Merlin replies, but Merlin replies with the same Z. Okay. So obviously you can see this, that this means that it is a Z, the probability of you fix Z. You fix Z, there is a Z such that probability of MXYZ is 1 with very high probability. But if Merlin sends the same z, same z as previous one, then this is the same as you always. So Merlin always sends this z. Okay, and for things for this z, the random bit string will have this high probability. So this means that at least have this kind of probability, this kind of fraction of bit string y will make this correct. So obviously that this implies this. Okay, so hopefully it's trivial. You can prove. You can just write down a definition, right? You can see this. It's obvious, right? If there is a z, then I always choose z to be here. Right, so this statement is actually implies this statement. Okay, so this one is simple. Right, so it replies the same message as SMA. Then by definition, this is just by logic definition. This is true. This is true. This is true. Okay, with high probability. So you prove that this implies this. Okay, so most difficult thing is I guess the difficult one is this part. Okay. Okay, so let me just prove. Write down proof. Okay, so recall in MA, right? Recall if X do not belongs L, right? If X do not belongs L, so this means that whatever message that Merlin sends, right? So that means that for all z, the problem of y that mxy z output 1 is very small. Now it's so small, such as this. Okay, so z is p of n, and the y is p of n. Okay, and so am is x belongs L, and then I want to ask the probability of y that there is a z, and m of x y z is 1 is less or equal to this. Okay, I want to claim that 1 implies 2. But if this is true, then I'm happy. Right, we finish the proof. Okay, so the proof by contradiction. Let's say 1 is true, and the 2 is false. Okay, if 2 is false, means that these guys, like let's say greater than equal to like 1 divided by 1/3, and you will see that this is very simple, right? So hopefully the logic is obvious. Okay, so for every z, you fix z, right? There is a probability y of this equals to y is less or equal to this. So I want to count the number of I enumerate all of y and all of z with length of Pn and the length of Qn, and I ask what's the number of mxyz accept, the number of it. Okay, or basically you can ask probability of yz, but I would like to use the number. Okay, and it's basically less or equal to what? Because for each z, right? So I have the 2 to the q of n z, and for each z, the fraction that y will make this accept is this. Okay, and I have like a 2 to the p of n of y, right? So I fix z, and for all of these y, there's this only tiny fraction. I guess it's 1, right? Okay, so basically this means that probably it's very small. Okay, so small. Okay, so this means that if you take the probability of yz of mxyz, right, that's equal to like 1 divided by 2 to the something. Or simply speaking, just maybe there's a I just want to say this is very small, right? So it's 1 divided by 2 of Pn plus Qn. Okay, so it's very small. Okay, but if 2 is true, right? Okay, so this is the 1, right? So 1 tell you this, right? Because you fix z, right? So the number of z is this, and then for all the bit string y, right? So with the length of p to the n, so you have 2 to the p to the n y string. The fraction of y string is basically this. So you just write down this. So for the number 2, if the number 2 is correct, this means that the probability of y is a z such that accept is greater than 1/3, right? So if number 2 is correct, then I fix y, there is a z, right? So this is greater or equal to something, right? I fix y, okay? So how many y I have? I have like 2 to the p of n y, right? And for all these y, there exists a z. The number of feeding number of the fraction that so for fixed y, there exists a z such that this is true. It's greater than 1/3. So let's say for each y, if this is 1, there's only such one z, right? This is the smallest case, right? So what I'm saying is that the fraction of y for fixed y, right, there is a z. So I guarantee that number of y, z, mx, y, z, for fixed y, there is a z at least 2 to the p to n divided by 3, right? Because I have this y, right? I enumerate all of y, and there at least 1/3 of y, there is this z corresponding to mx, y equals to 1. So I get 2 to the p n divided by 3, right? Contradiction. Because 2 to the p n divided by 3 is large, but this is 1 over 2 to the p n plus q n, which is this is 1, very small, as n if n goes very large. Okay, so contradiction, this is small, this is large. Okay, so this is the proof. Basically, you just use the arrow, you just increase the arrow, and using this just counts the definition. You just write down the definition. It's basically there's a logic that you need to worry, but it's simple. Okay, and the next video that I want to show that I think AMA is in the sigma 2 and pi 2, and I want to show that AM is in the pi 2. Okay, so basically this is the class that we define the polynomial hierarchy. Okay, so we want to relate AM in the MA to the polynomial hierarchy. Okay, and the proof is very simple, just using the idea as the same as we proved in the PVP case. Okay, see you next videos.